Now we're ready to look at a two-proportion type of test. And now we're going to look at a setting where we have two populations. One population has a true proportion of P1, and the other population has a true proportion of P2. And we're going to take simple random samples of size n from this one and a simple random sample of size n from this one. These don't necessarily have to be the same sample size. And then we will get a p-hat, and from here we'll also get a p-hat. And what are we going to do? We're going to subtract these p-hats. And if we do this over and over and over again, remember we get a sampling distribution for the difference between these p-hats. Now, what should the mean be if I continue to get groups of n1, n2, and calculate the proportion of each one? If I subtract these pairs over and over and over again, continuing to take samples of the same size, then these differences will center at what the actual difference is between our parameters, and the sampling distribution for these differences will not always have the same value here. There will be a standard deviation associated with these. And remember, when we're dealing with sampling distributions, if we want to find what is the variability when we're subtracting two random variables, we have to add their variances. And this is the variance of the first sampling distribution of p-hats, and this is the variance of the second sampling distribution of p-hats. And so if we want the standard deviation, we could square root. All right, so let's look at what characteristics, if we're going to sample these and try to find out if there's a difference between the two. Let's look at our assumptions and see what's different here as opposed to in the previous section. So we definitely want to have two populations in which we're taking two simple random samples. Now, just like in the other section when we're doing a one sample or one proportion z-test, we want to have our population of the first group, and there's a capital N1 is the associated number of total people or things in this, and this one has capital N2. We want the populations to be greater than or equal to 10 times the sample size, and that's so we can use that type of standard deviation formula. Now we have a test to see, do we have an approximate normal distribution? And our test here is to find, is our actual number of successes, actual number of failures from the first population, actual number of successes, actual number of failures from our samples, our two samples, are they at least 5? So that is different. The previous type of test where it was a one sample test, to do a confidence interval, we had to have the actual number of successes and failures be at least 10. Now we can go as low as 5 when we're comparing two distributions. And here is our formula for calculating what the confidence interval is for the difference between these two proportions. All right, so we're going to look at this example. And so I have our setup here where we had in 1995, we were looking at the proportion of people who were smoking cigarettes, and we had 550 white adults and we had 550 black adults. And we found from those samples that 25.7% of the black adults smoked versus 24.8% of the white adults. And we want to find a 90% confidence interval for the difference between those two groups, because obviously these samples are different numbers. But what is the confidence interval for that difference? The idea that if we continue to take more and more samples, each of size 550 from each group, what kind of difference do we really expect to get in terms of an interval estimate as opposed to a point estimate of these two particular numbers? Now, we have three things we check. First of all, do we have simple random samples? We don't really know that, so we'd have to be careful about using any of this information based on not being told where these numbers are coming from. Hopefully they're credible. Secondly, we want to see, do each of our populations have that characteristic of being greater than or equal to 10 times the sample size? And we could definitely get at least 5,500 people who could participate in each of those two groups. Thirdly, we want to look, is our actual number of successes and failures at least 5? And so if I do a little multiplication here, in both cases I would anticipate that they must have had 136 successes and about 414 failures, because we know these would have to be actual numbers. If they were sampling from 550 people, it couldn't have 136.4. And likewise, same thing over here with the black adults. We must have had 141 successes and 409 actual failures. All right, so all of our successes, actual number of successes and failures, were at least 5 by a long shot. So now we're ready to calculate our confidence interval for the difference between these two. So what we got, plus or minus, I used the z-star value for 90%, and then here is my big standard error. And I have the p hat, 1 minus p hat over sample size. That's the variance of the first population. And p hat, 1 minus p hat over the same sample size. And this whole big hunk here is again called the standard error for the difference between those two distributions. And I get that confidence interval. Now, how do we perform hypothesis tests? And for a hypothesis test, we are going to be assuming, in this type of circumstance, that our two proportions for our two populations are equal. So we're going to assume that these two numbers are equal values, or that the difference between them is 0. So our sampling distribution, we're assuming, is centered at 0 for the difference between these two proportions. Likewise, we would like to have two simple random samples from the two populations. Number 2 is the same as well, and again, so that we can use that standard deviation formula. But now we have this test is a slightly different than the previous one. We have a new concept called a pooled p, and let me explain where that comes from. We are going to be assuming that these two numbers are equal. And in order to calculate the standard error, we need to know what are these two equal to. And we are going to call the number that they're equal to the pooled p. And we will put a p hat on it. So anytime you see a p hat without a subscript, when it's a two proportion z test, the p hat all by itself is going to be the pooled p. And so how do we find the pooled p? Well, I'll show you in one moment. So let's look down at our example, and we'll come back up and look at this little characteristic and this formula. All right, so we have, using the data from the previous page, do we have evidence to show that the proportion of black adults who smoke is significantly higher than the white adults? So I can see that significantly higher. I'm going to do a one-sided test. So I'm going to assume that these two groups have the equal proportion for smoking. Okay? Assuming they're equal and that their difference is 0. So I know my picture is going to be centered at 0. And alternately, that I'm thinking that this group has a higher proportion than this group, so that that difference would be a positive value. So we know we have two simple random samples, and we know we have at least 5,500 people in each group, so we're good to go as far as the standard deviation formula. Now do we have a distribution that's approximately normal? Here's where we have to calculate the pooled p, and again, that's what we're going to assume that these values are equal to. Now, we know from the original sample that this was the proportion of people who were in one category, and this was the proportion who were in the other category. So this was how many people we had in the white adults who were smokers, and this is how many we had in the black folk for the smokers. So to get the pooled p, we're actually going to take all of them together, the entire group of 1,100 people, and look at how many total successes, because we are pooling them together. So we're going to assume that these two are equal, and we're going to assume that they're both equal to 25.18%. So now, going back up, we want to find how many do we expect to get that are successes, failures, successes, failures. And so we want all of these to be at least 5, but I don't use the proportions I use my sample size for the black adults was 550 times the pooled p of 0.2518 gives me this as my expected number of successes, which actually will be the same as the uh, value for the white adults as well, since we had the sample sizes being the same. And for both groups, this is how many failures I expect to get. So my expected number of successes and failures are at least 5 based on using my pooled p. Now I'm ready to calculate and draw my picture and get my test statistic and so on. So I have my picture, as I always draw, centered at 0. Now what did we actually get? Well, the differences between those two proportions was actually 0.9% or 0.009. And we need only to find this one tail because we are doing a one-tail test. So what I'm assuming, plop down what I actually got. Now, we have two ways we can calculate the test statistic. We take what we got minus what we're assuming. We're assuming the difference is 0, so I didn't even bother writing it down. And now, we'll go back up here a second. When we're calculating the test statistic, we're going to use, for our standard error in the denominator, we're going to use our pooled p as the assumed value that these two are equal to. So I use the pooled p here for the first group. I'm assuming that it's actually equal to, in our case, 0.2518. So the number, 1 minus the pooled p over the sample size. And then we have the other population that has the number, 1 minus the number over the sample size. Now, these are always going to be the same when we're doing a hypothesis test because we're assuming that both these proportions are equal to the pooled p. So these can be factored out to arrive at this fraction. So these two are both equivalent. Let me add that little parenthesis right there. So in the bottom, I use the factored version, which doesn't necessarily have to be used. You could use the other version of the formula. And so I have what I got minus 0, because that's where I'm assuming that the picture's centered. And then I have down here the factored version. This really could be the same as writing this times this over 550 plus this times this over 550 if it were distributed through. The test statistic is calculated to be this value. And just like normal, I find my p-value, and I make my decisions the same way. This p-value at any significance level is not considered significant. We have no evidence that the proportion is higher. It appears as though there is absolutely no difference. That's just random variability for a distribution in which the two proportions are equal. So that's kind of a fast version of going through, but I think you'll be all set. So you're ready to practice.